Hello, James Flaten here with Minnesota Space Grant. This is part 2 of a 3-part series about calculating static margin for rocket stability. In part 1, we saw some equations for doing such a calculation. Now let's actually see what that looks like if I do it on paper. Again, the long and short of it is calculations of this sort will actually be done for you using OpenRocket or RockSim, but I think it's valuable to see what goes on behind the scenes. So let me switch over to another camera and let's just do this calculation. So here we go. I'm going to call this sample CP and G and static margin calculation. So using my grid paper here, I'm going to draw basically the simplest rocket I can think of. And if each unit on the grid paper is 1 inch, let me draw a rocket that has a nose cone. The rocket will be 2 inches across, and the nose cone will be 4 inches long. And then let's say that the rocket body itself is 10 inches long. 2, 4, 6, 8, 10. And then let's say that we have some fins. And so the fins will be, let's say 3 inches tall, have a 2-inch tip, and stick out 2 inches. So they'll stick out 2 inches, there'll be 2 inches at the tip, 3 inches at the leading edge, and let's say that I have 4 of them. Okay, and it's a cylindrical nose cone. So basically, I'm sorry, it's a conical nose cone. So if I have a conical nose cone, 4 inches tall, 2 inches diameter at the base. And I need to know how heavy it is, so I'll say it weighs 3 ounces. Okay, so here's the body. And the body will be cylindrical. We talked about the body being 10 inches tall, 2 inches in diameter. And let's say that it weighs 4 ounces. And let's just say that that's evenly distributed. So there's the nose cone there. There's the body there. And now the fins. So I have 4 clipped delta fins. So that means n equals 4 for our calculations. The root length was 3 inches. The tip length was 2 inches. The height is also 2 inches. That's how far they stick out. The sweep in this case is 1 inch. That's how far it is from the beginning of the root to the beginning of the tip. The radius of the body is 1 inch. The diameter is 2 inches. So those are body details. These are fin details. The distance from the middle of the root to the middle of the tip would be called L. And you can calculate L as 2.06 inches, just for this geometry. Okay. And let's just say that we have 4 fins and they weigh 1/2 ounce each. So I've set the stage. Now it's time to calculate some things. So I'll just keep that kind of nearby. In fact, can I keep that in sight? Yeah, I can. Let's do our center of gravity calculation. So I guess I need to draw the rocket again. So here we go. 4 inches long, nose cone. 10 inches long, body. Fins stick out 2 inches, sweep 1 inch. So there's my body. And this was the line with respect to, or where I will be making all my measurements from. So in this particular case, presumably I have a location of a center delta x c g n. That's my location of the center of gravity for the nose with respect to the tip of the nose. And then I might have a distance from the beginning of the body to the center of gravity of the body. So that would be called delta x c g body. And then of course the body itself is some distance from the 0 point. And then I have the beginning of the fins here. And let's say that for a given fin, I have a delta x fin. So that would be c g fin f. Okay. So that is how far it is from the beginning of the fin to the center of gravity of the fin. And then of course the fin itself, xf, that's how far it is to get to the fins from the 0 point. So now that we have set up our variables, let's start doing some station calculations. So for the nose cone, the station, so that's x bar, c, g, n, in this case, n stands for nose cone. This is a conical nose cone, so it's 3/4 times the height of the nose cone. Height of the nose cone is 4 inches. So that turns out to be 3 inches. And then remember the weight of the nose cone was 3 ounces. Okay, so those are values on this page. How about for the body? Well, remember that this is symmetrically weighted. And so the station, CG body, would be equal to the distance to the body plus the offset, CG body, okay? And the distance to the body, well, is just the height of the nose cone. So that's 4 inches. And the offset is half of the length of the body. So that would be 1/2 times 10 inches. So 4 plus 5 inches, I have 9 inches. So it's 9 inches from the very top here, 9 inches from the very top to the center of gravity of the body. Okay, that was easy enough. How about a fin? Just one fin. There will eventually be 4 of them. Okay, so let's figure out how far it is to get to the fin in the first place, xf. Well, it turns out one way to calculate this would be to say the fin is the fin starts here, and so that would be the entire length of the rocket minus the length of the fin. That's one possible calculation. So how about I say xf is equal to xb plus the length of the body itself. So xb is the distance to the body. How about I call the length of the body itself? I don't have it on my value here. Actually, I have it way over here. Actually, I don't have a variable for it. 10 inches tall, right there. Okay. xb plus 10 inches minus a. Okay, I just didn't bother assigning a variable to the length of the body too. A is, so xb plus 10 inches minus a would get me to there. That's fine. So this is 4 inches plus 10 inches minus 3 inches is 11 inches. That's how far it is to get from here down to there. And now I need to figure out how to calculate this distance, x, CG, for the fin. Okay, that's one of those complicated equations. I'm going to move over here just to give me a little more space. Delta x CG for the fin is equal to, from the slides, b squared plus 2/3 m squared plus 2mb divided by 2b plus m. So this will be a distance in inches. So I have 2 squared, that's b squared, plus 2/3 1 squared, because m is 1, plus 2 times 1 times 2, divided by 2 times b, which is 2, plus m, which is 1. And that entire thing will be in inches. That happens to be 1.73 inches, if you run the numbers. Okay, so with that in mind, here's what I've figured out. The station x CG for the fins, okay, will be how far it is to get to a fin, 11 inches, plus 1.73 inches. That's how far into the fin you have to go to find its CG. 12.73 inches, and remember the weight of a fin was 0.5 ounces, half an ounce. Good. Yep, almost done with this part at least. The total weight, fins still. W total fin is n, the number of fins, times W for one fin. Okay, and so that is 4 fins times 0.5 ounces for each fin. Okay, is 2 ounces. So that's the total weight of fins. And now the total weight of the rocket. Very simple rocket. Most rockets would have more parts than this. Okay. Well, this would be the weight of the nose cone, 3 ounces, plus the weight of the body, 4 ounces, plus the weight of the fins, all of them, 2 ounces. So I put that together, 3 and 4 is 7, plus 2 is 9 ounces. That's an important number. Now I need to sum the CG station times the weight for each part. Okay, and that's going to equal the final overall CG times the overall weight. Okay, so for the nose cone, the station was 3 inches right there. I'm sorry, yes, the station was 3 inches. And the weight was 3 ounces. For the body, the station is 9 inches multiplied by 4 ounces for its weight. And for the fins, there's 4 of them at half an ounce each. So the station was 12.73 inches times 4 times 0.5. That's 4 half-ounce fins. Add this all together, and I get 70.47 inch ounce. So if I'm really interested in this is the average CG. All I have to do is take 70.47 inch ounces divide by 9 ounces. 70.47 inch ounces divided by 9 ounces, and I will get 7.88 inches. And remember, this is measured down from the tip of the nose cone. But let's see if that makes some sense. So it's almost 8 inches. The over here in my figure, the nose cone is 4 inches long, and so it's going to be down here somewhere. That sort of makes sense. Somewhere in the middle of the body, well before you get to the fins. That's the balance point for the rocket. Okay, now I'm going to do exactly the same kind of a calculation, except I'm going to do it for center of pressure. So I think I'll leave this page up. And the reason is my center of pressure calculation will look a lot like that, for starters anyway. Here we go, CP calculation. I'll draw my rocket. It's always a good idea to have a drawing of the rocket nearby. 4-inch nose cone, 2-inch diameter, there's 10 inches long for the body. Here come the fins. Still going to make all my measurements from up here. So in this case, I'm interested in how far is it to the center of pressure for the nose cone. So I'll call that X CP nose cone. How far is it to the center of pressure from the top of the body? Actually, I think I should have called that delta X. Delta X here. How about this is called delta X CP for the body. And of course, I already know the distance here, XB. And then for the fins, how far is it from the top of the fins to the center of pressure for the fins? And I've already calculated the distance to the fins, XF. So, nose cone. The distance into the nose cone for this shape of nose cone is 2/3 times the length of the nose cone. Okay, so that would be 2 2/3 inches. And the coefficient, the normal coefficient for a nose cone is 2, nose cone of this shape. Here comes the body. Aha, but remember, since the normal coefficient for the body is 0, I can skip this. So I don't even have to worry about that number, although I know the answer. It's half the length of the body tube. But it's not going to come into this calculation because it has no sideways impact on airflow. Okay, so here we go. One fin. I'm interested in how far is it to the fin? And the answer is, we already figured that out, XF. 11 inches, calculated before. And now I have to calculate this piece. Give myself a little more space here. Delta X CP for a fin is equal to M A plus 2B over 3A plus B plus 1/6 A plus B minus A times B over A plus B. That's from the slides. And so now let me just put in numbers, and eventually this will also always come out in inches. So I have 1 times 3 plus 2 times 2 over 3 times 3 plus 2 plus 1/6, 3 for A plus 2 for B minus 3 times 2 over 3 plus 2. And this entire thing will be inches. This turns out to be 0.46 recurring. This turns out to be 0.63 recurring inches. So it's 1.09 inches. Again, that kind of makes sense. This is 3 inches tall, and so a little bit over 1 inch in is the location of the center of pressure for each fin. So that said, the station center of pressure for the fin is going to be equal to 11 inches to get to the fin plus 1.09 inches into the fin. It's actually 0.9 recurring. And so 0.9 recurring is the same thing as 1.1. So this becomes 12.1 inches. Good. Now I need to figure out the normal force coefficient for one fin, and then eventually the normal force coefficient for the set of fins. Here we go. Fin continued. So the normal force coefficient for one fin is equal to 4 times n times s over d squared divided by 1 plus the square root of 1 plus 2L over A plus B. And then I take that entire thing and I square it. That's just the equation. A little bit of a nuisance, but again, if you were to code that into Excel, once you've coded it in one time, you can use it forever. Let's do it. 4 times 4 fins times S. S is how much they stick out. That's 2 inches. Divided by D, the diameter of the body, which is also 2 inches. So that's convenient. Ultimately, this is going to be a unitless number. 1 plus square root of 1 plus 2 times 2.06, that's L, divided by 3 plus 2. You just square that, add 1, and then take the square root. Run the numbers, 6.97. Now that I have one fin, now I want to figure out what is the impact of having this one fin offset. So now it's time for the body interference factor. So the body interference factor K, okay, for the fin and the body as they relate to each other, is defined as 1 plus the radius of the body divided by S plus R. So this is going to be a number greater than 1. 1 plus the radius in this case is 1, S is 2, plus 1. So it's 1 plus 1/3. Okay, so that just becomes 1.3 with the 3 recurring. And so now I have to adjust the fin, adjust the coefficient. Okay, so Cn fin body is K fin body times Cn for one fin. So that's 1.3 recurring multiplied by the 6.97 that I had up there. That gives me 9.29. So that's the normal coefficient for the fins, considering they're set off from the body. Good. Now, if I want to calculate the average location, I just need to do the following. Total normal coefficient this is sort of like the total mass in the previous calculation. Okay, so here Cn total is, I'll go back, it's 2, that's for the nose cone, plus 0, that's for the body, plus 9.29, that's for the fin. Okay, so that becomes 11.29. And now, sum of CP station times the normal coefficient. That will be the overall CP station times Cn total. That's the overall location, the overall coefficient, which I just calculated, is equal to this sum. So this sum, looking back, would be here it is, 2 times 2 2/3. 2 2/3 happens to be 2.6 recurrent. Okay. So how about I have 2 times 2.6 recurring inches plus 0, the body, plus 9.29 times 12.1 inches, that's for the fin. Add this all together and I come up with 117.7 inches. And thus, wait for it, the location of the center of pressure for this object overall is equal to 117.7 inches divided by 11.29. 10.43 inches, again measured from tip of nose cone. Okay, so remember we found the value for the location of the center of gravity measured down. That was 7.88 inches. And now we have the center of pressure, 10.43 inches. This is good. It's bigger than the center of gravity number. So that means my static margin is going to be a positive. So let's just calculate the static margin. Sm is equal to the distance to the center of pressure from the tip minus the distance to the center of gravity from the tip divided by the diameter of the rocket. Okay, so I have 10.43 minus, from my previous page, 7.88 divided by 2 inches equals 1.3. That's good. So this would be considered stable. So just a reminder, and that is, if the Sm is negative, it's unstable. If the Sm is from 0 to 1, how about greater than 0 to 1, that would be considered marginal. It's stable, but it's not great. If the Sm is greater than 1, that's good, that's healthy, okay? So we're going to call that stable / healthy. On the other hand, if the Sm is greater than some number, 2.5, some other people use an even higher number than that. 2.5 is what Barrowman suggests. That could be considered overstable. Okay, that's the calculation. It took a while. Now let's do it in Excel in the third recording.